suppose you observe data that you know is going to be coming from a binomial distribution. So it has the form f of y given tau is equal to n choose y, tau to the y, 1 minus tau to the n minus y. The shape, you note, depends on tau to the y, 1 minus tau to n minus y. And furthermore, tau is an element of 0, 1. Sorry, is in that interval. Note the use of square brackets as opposed to round brackets. Remember, in maths, all your brackets mean certain things, so use them quite carefully. So, the binomial distribution is a member of the natural exponential family of distributions. That's quite a fancy way of saying it can be put into the form f of y is equal to the exponential of theta y minus b of theta over a of phi plus c y given phi. However, that's for another course. Knowing that it is a member of the exponential family distributions means that you know it has a conjugate prior. So that's a prior that has the same distributional form as a posterior. So knowing that it exists is a really good place to start. There's no point in hunting for one if they don't possibly exist. So, given that it exists, you're thinking about what of your distributions that are valid on the interval 0, 1. And actually, of the exponential family, there's really only the beta distribution, other than the binomial distribution. That's actually a possibility. So let's consider the beta distribution. So beta AB distribution. Because it's valid also on the interval 0, 1. So the form of the beta distribution is beta AB is equal to gamma A plus B over gamma of A, gamma of B. And as we chose the letter earlier, we'll stick to it. M to the A minus 1, 1 minus M to B minus 1. That's the general form. However, we're considering a prior for a random variable tau. So it's for our parameter tau. So instead of it being m, it's going to be tau. So g of tau is equal to gamma A plus B, gamma A, gamma B, tau to the A minus 1, 1 minus tau, B minus 1. Okay, so we're getting places now, because how did we find our posterior distribution? Well, it's what's it proportional to? Times likelihood. So it's the posterior is proportional to prior times likelihood. So that means, and we're only going to be worried at this point up to the constant of proportionality. We'll worry about that at a later point. So that means we can essentially ignore all this bit. So it's proportional, because that's just a constant. So we don't need to carry around constants with us. So it's proportional to tau to the a minus 1, 1 minus tau to the b minus 1. And we've observed data, our likelihood is of this form here, with n minus y being constant with respect to tau, so we can ignore that bit. So multiplied by tau to the y, 1 minus tau, n minus y. That's a y. Okay. Now what's your natural inclination? Hopefully it should be to group like terms together. This is proportional to tau to the a plus y minus 1, 1 minus tau, b plus n minus y minus 1. Can anybody tell me what distribution that is? And does it help if I do this? It's not quite the binomial. Look back over what has some letter. So tau to the power of some letter minus 1 times 1 minus tau to the power of another letter minus 1. Well, it's the beta distribution. But instead of having a, we now have a plus y. And instead of having b, we have b plus n minus y. Now think about it. What does y represent? Y represents the number of successes. N minus y represents your number of failures. So it's saying there's a very easy updating rule. You start off with a prior, you observe some data, you add your number of successes to the a first parameter and your number of failures to your second parameter, and that's it. You're done. And this is where you really see the advantage of having used a conjugate prior. So it's beta a plus y and b plus n minus y distribution. Formally you can go, it's gamma of a plus y minus y, so that's going to cancel out, plus b minus plus n. So divided by gamma a plus y, gamma b plus n minus y, over to the times tau to the a plus y minus 1, 1 minus tau to the b plus n minus y minus 1. And that's sufficient to show that the beta prior is a conjugate prior for the binomial distribution, for binomial likelihood.